robo analyzer. Now I'm going to share my screen. Okay.
Yeah, now it is visible, sir. Thank you, Professor.
Yeah. But that software is not opening, sir. That
No problem, sir. Please continue what you want. Okay.
UI path is not opening. Okay. So, once again, and sorry for the disturbances. Actually, I'm not at NIT Jamshedpur School. I went to my in-laws' house, and here I'm delivering lecture from here. So that's why a bit long. Okay. Regarding this robo analyzer, as I told you, it is a 3D model visualization. The robo analyzer is a 3D model based software that can be used to teach and learn the robotics concept. It is an evolving product developed in Mechatronics Lab, Department of Mechanical Engineering at IIT Delhi. And I have interacted many times with the concerned professor, the concerned students at that time. It's a development started under the guidance of Professor S.K. Saha, Subir Kumar Saha. He was ex-HOD in the Department of Mechanical Engineering, IIT Indore. In order to support the learning and the teaching of the topics covered in his book, Introduction to Robotics, it is very nice book. So, and his team developed this software, and this software is for the software exposures of kinematics and the dynamics of a robot. Okay. So they named this software priceless software as it has immense value for a zero cost. The developers believe that free software world had lost its value, and hence the new term. Okay. Now, this anyone can search in Google, and the website name is www.roboanalyzer.com. Okay. So we are here at home page. So it was a little bit about the software. It is good for the virtual experiments using RoboAnalyzer that can be used to complement our robotic courses. Generally, having actual robots in the lab are difficult due to funds, space problem. So why not to have, in that case, why not to have some software exposures? Okay. So how to download? One can go here in the download. Then you'll find RoboAnalyzer is developed using Visual C and OpenGL, and it can be currently run only on Microsoft Windows. Okay, these are the system requirements like processor, RAM, operating system, dependencies. Now, which one, if you ask which version we have to download, so obviously the latest version. Okay, and what about the other versions? And why latest version we should download? Because it had the added features like in this homogeneous transformation matrix. Okay, so what is this homogeneous transformation matrix? You will see in that software and how the values are being changed as per the movement of the robots. Okay, so homogeneous transformation matrix. So what is the transformation? Very first, transformation is the movement one point to the another point. Okay, and from that object, a robot either can translate along the axis, either can rotate about the axis, or it may have both translation and rotation about the axis. Okay, so we need to map that movements. Okay, and we need to take a reference. From that reference point, we need to measure the what are the positions of the robot tips. Means what is the configuration of the robot, and what is that configuration? Configuration means the robot's position plus orientation. That is the configuration. And the transformations means movement of the objects. Okay, and there are three types of transformations: pure translation, pure rotation, and the third one, translation plus rotation. Okay, now it's okay. Transformation matrix, we know why here matrices are required. Matrices are required so that we can get the final pose or configuration of the robot. Means where is our end effector? End effector means the something, the tool attached at the wrist of the manipulator. It is our wrist, so that is our end effector. So what about the position and the orientation of the end effector? Okay, that can be known by the multiplying these matrices. Okay, now why it is known as homogeneous transformation matrix? Homogeneous, why? Because if you multiply matrices one to another and another to further another, okay, so what should be? The dimension should be in matching. Okay, like all the matrices should be in the same dimensions, like a 3 by 3, 4 by 4, or 2 by 2. But generally in the homogeneous transformations, it will be 4 by 4. Okay, so homogeneous means square matrices. All matrices should be in square, means the number of elements in the rows should be same like number of rows, number of elements in the column. Okay, so these are the extra features added with this software. So you can see the evolution of this software from where it was started. In the very first version, Robo Analyzer V1, what was the features? The forward kinematics of revolute joints, animation, and a graph plot. Okay. Now, after the time being, see, forward kinematic of revolute plus prismatic joints. Okay. So, what is that? A prismatic joint? The joint which is responsible for the translatory motion. revolute, rotary motion. Okay. In the next version, this Robo Analyzer V2, the added advantages were these prismatic joints and visualization of DH parameters. Okay. So DH parameters visualizations, DH, the full form of DH is Dana Wade Hartenberg. It's named after two scientists, Dana Wade and the second, the Hartenberg. Okay. So after time being, it got featured with more. Okay. So I downloaded this one, the latest one, Robo Analyzer V7.5. Okay. So now I'm going to access the software which I have saved here. Robo Analyzer, you can see. Okay. Please confirm me the screen is visible or not, because earlier I had problem. So now I'm going to click the Robo Analyzer STM module. Okay. So what is this actually? I'm going to click it and now it is going to open. You can see here the STM module. STM means homogeneous transformation matrix module. Okay. And see, if you see, there are two coordinate systems and both are coinciding to each other. Both are coinciding to each other. Okay. Now, if you see the left side, right side, so right side, there are two terms, local and a global. Okay. So local and a global. So how to know the positions of the end effectors of the robot? Okay. And with respect to from where? Okay. So local means we are mapping the you can say positions in this workspace. You can say, suppose we have a put some coordinate system at the origin of the robot. Origin means the base of the robot. Okay. And with respect to that, suppose we are going to measure the last link, measure the positions and the orientation of the robot of the last link. So with respect to that, the absolute frame at the base of the robot, so that will be the local one. Okay. And suppose we are going to measure the base of the robot somewhere, some other places. Okay. So suppose here one coordinate system is here, and here one coordinate system is, and this is the base of the robot. Okay, and we want to know the coordinate system here at the last link of the robot tip. Okay, so it will be global with respect to the first coordinate system. Visualize the three coordinate system. Okay, suppose this is the first coordinate system, this is the second coordinate system, and this is the third coordinate system. So this third coordinate system with respect to the second coordinate system, that is the local, and this third coordinate system with the first coordinate system, that will be the global. Means globally we are going to measure, we are going to know about the positions and the orientation of the robots. Okay. So this is for reset. For resetting. Yeah. Okay. We want suppose this isometric. Initially, we want isometric view. Okay. Now we want to see the motions along the x, y, and the z axis. So I'm putting value of 2 in the x-axis, x is equal to 2. Now see the changes. Okay. The another coordinates system got moved along the x-axis by 2 unit. Okay. Resetting it. Now visualize along the y direction. Okay. Uh, Better if you visualize this by putting x is equal to 0 value. Okay. Now see. So this green color is for y-axis, this red x-axis, and blue is for z-axis. Okay. So again resetting it, y is equal to 2 I am putting. Now we want to see the motion in the z direction. So putting value 2 or suppose 3. Okay. See. So these are the motions along the axis, and the motion is which kind of motion? It is a translatory motion along the axis, and it is due to the prismatic joints, not due to the rotary joints, rotary or revolute joints. Okay. Now, yeah. Now, globally, suppose we want to see the motion along the x, y, and x I am putting suppose 4. Now see what is happening. It is not along the x-axis. If we measure globally. Okay. Now resetting it. Now and see the changes in the values in this matrix. And this is the homogeneous matrix, homogeneous transformation matrix. Whenever we are going to change values of x, y, z, it is being changed. And the same for rotations. Now we want to visualize the rotation about x-axis. Okay. So suppose I am giving value of 30 degree about, and we want to know rotation about x-axis. Okay. So see, after clicking this rotate, and see the movement in the coordinate systems. Again I'm rotating, again I'm rotating, again I'm rotating. See, if you observe closely, the rotation is about x-axis. Okay, and both the x-axis of the both the coordinate systems are coinciding to each other, but the other axes are moving by the same angle, 30 degree. Okay, like about y-axis is moving by 30 degree, rotating by 30 degree, and also z is rotating about 30 degree. But x is rotating about its own axis. Okay, that's why both are coinciding to each other. Now we are resetting it. We want to know rotation about y. So there will be rotation in x and the z axis. Okay. Again we can rotate 30 degree again. Okay. Now we are resetting and we want to visualize rotation about z axis. And suppose I am putting here 60 degree. So see the rotation in the axis. Okay. And accordingly, this homogeneous transformation matrix, the values of this matrix are being changed according to the rotations in the axis or translations in the axis. So if you see the left side and the top, they are the transformations. So transformation, as I told you, translation, pure translation and the pure rotation. And the third may be the translation plus rotation. Like suppose there is a translation along the x-axis, so it got moved, the frame got moved 2 units along the x-axis. Now, we want rotation about the same axis, and suppose 45 degree rotation we want. So it got now rotated. It is the third type, translation plus rotation. Okay. Now what are the sequences? View, the isometric view. This is the isometric view. Also we can see the XY plane. Okay. Z got removed here. If we want to see that movement in the XY plane or XZ plane, so how it will look like. Okay, and undo all zooms, and by resetting same the initial values we will get. Okay, so this was a little bit about the coordinates, the exposure of coordinates, how it got moved from the one point to the another point along the axis, and how it got rotated about the axis. Now I am moving towards, now I am clicking this Robo Analyzer, the another application. Okay, so it is the 3D model robot, and if you see the below DH parameters, so DH parameters, what it is? Dynamite Hartenberg parameters. Like for this a simple robot, easily we can know the positions and the orientation of the robot. Okay. For this, it is a 2 degrees of freedom. You can see degrees of freedom left side. It is 2 degrees of freedom, and select a robot. So which kind of joints here? So both the joints are the revolute joints. Okay. So if you want to know the positions and the orientation of the robot, so for this simple robot, easily we can get. Okay. How to get? Suppose for x tip, you want to write the tip position equation. So what will be? X is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2. Okay, similarly, for the y direction, the cos term will be replaced by the sin term. Okay, and similarly for z direction. And what about the orientation of the robot? So the orientation will be the summation of all the angles. Like the theta will be theta 1 plus theta 2. So easily we got the kinematic equations for this. But what about the complex kind of robots like a 7-degree freedom robot? Yeah, this kind of robot where number of more axes are involved. So can we get easily the kinematic equations? No, easily we cannot get. Okay, for and what is that kinematic equations? Kinematic means we want to know about the position, velocity, and accelerations of the robots. For the computer science people, no need to worry about how to get the kinematic and the dynamic equations. Okay, but if you write the coding, so that coding comes from that kinematics and the dynamic equations. Okay, so what is the kinematics? In the kinematics, we study about the positions, velocities, and the accelerations of the robot. We don't bother about the causes behind the motions. Like in the linear case, the force may be the responsible for moving the joints, moving the manipulator, and for the angular motion, that torque is required to move the manipulator. Okay. So why these DH parameters are required, or you can say the DH convention is required. And what is this? The DH convention is just like is getting you can say for getting kinematic equations of the manipulator. Okay, as I told you, for the simple robot, easily we can write the position, velocity, and the acceleration equations. But if a robot becomes multi-axis, more number of degrees of freedom will be there, like a 20, 30, 40, or the mixed kind of robots, like a prismatic joints, rotary joints. Okay, then in that case, we need to go with the DH convention. Okay. So DH convention, once again, D denotes the derivate and H denotes the Hartenberg. Okay. And there are four parameters: the joint offset in the case of prismatic joint, joint angle in the case of rotary joint, link length, and the twist angle. Okay, link length and the twist angle. Suppose both the axes are not in parallel. Okay, both are intersecting to each other, like this one. So how much it got twisted. So whatever the angle will be between these two axes will be the joint angle. Okay. So in these parameters, there are four parameters. Once again, the joint offset, joint angle, link length, twist angle. Okay. Joint offset in the case of prismatic joint, joint angle in the case of rotary or revolute joint, link length is the length of the link. Twist angle, as I told, if both the axes will be intersecting to each other at somewhere, then the angle between those axes will be known as the twist angle. Okay. Now initial value and the final value. So initial value means before uh, motion of the manipulator, and the final value is after the final, means after the motion, where is our manipulator. Okay. Okay. Now, so this was a little bit about DH parameters, and you, you can see here there are number of default robots like 1 degree freedom, 1, 2, 3, 4, 6, 7, and select robot types like for 7 degree freedom only we have SRS. This is the robot name, model name. Suppose for 5 degree of freedom robot. Okay. So see, 5 degree of freedom robot, we can have all the joints as revolute or the prismatic revolute combination, like this one, like this one. Yeah. You can see how many joints are there, means how many degrees of freedom, 5 degrees of freedom. Okay. And what about the joint types? So P denotes prismatic, R denotes revolute. So total 3 prismatic joints are there, and 2 revolute joints are there. Okay. Now we want to visualize its motion based on the inputs, and these are the inputs like a joint offset, joint angle, link length. These are the inputs. Okay. Now we want to know the motion. So before that, before clicking this F kinematic, forward kinematics and the inverse kinematic. If you see forward kinematics and the inverse kinematics. Okay. So what is this? The forward kinematics for the given set of joint angles. You can see joint angles. For the joint 1, it is 90 degree, for 2, 90, and the 3, it's the 180 degree. Okay. And what about the other? Others are variable. Okay. So, for the given joint angles, or you can say joint inputs. Okay. If you say joint inputs, then there may be prismatic, either prismatic or revolve. So for the given joint inputs, what will be the position of the robot and effector? Okay. Means where will be our and effector? And this is the and effector. Okay, so where will be for the given set of joint angles, joint offset. Okay. So that is the forward kinematics. And now I'm going to click forward kinematics. Now see the motion. It got analyzed. Means now we know about its positions and the orientations mathematically, but we want to visualize it's a motion, then we need to play this forward button and now see the motion of the robot and effector. Okay. And which kind of trajectories are given to the end effector. So here it is quintic. Okay, why not to give suppose a cubic. So suppose we have given here cubic and the forward it comes to the initial position and now we are going to analyze forward kinematics and then playing it. Now see the motion and the trajectory type is cubic type of trajectory. Okay. And what is that trajectory? Trajectory is that time dependent equation. Sometimes we say path, but that is not correct. Path is the time independent. Okay. In robotics, we bother about the time and the speed. So the exact term is trajectory. Okay. So uh, these the path traced at the time being path traced by the robot tape is known as the trajectory. Okay. Now, forward kinematics we have done. Forward kinematics is for the given joint inputs, what will be the robot tape position, okay, and the orientation. What about the inverse kinematics? Now, we need to think in the reverse way. Earlier, the inputs were the joint angles or joint offset. But here, and the output were the robot tip positions. But here, the output will become input and input will become output. Like in inverse kinematics, as I told you, the joint positions will be defined, will be given. Okay? And then what will be the joint angles? What will be the joint offset? That we have to know. Okay. So the beauty of inverse kinematic is we get multiple solutions. Okay? Means to reach the same point, there are number of ways. Like this hand sanitizer, I am going to handle it. So either I can go through this way, my hand can go through this way, it can go through this way, or it can go through this way. Means there are a number of solutions. Okay. Yeah, just yeah. If you have any queries in between, please you can ask.
Sir, in chat box,
Yeah.
can you share the HTM module to us? One of the Ajay Venkateswar is asking, sir.
Uh,
HTM module.
yeah, HTML model. Yeah, that link I can share you, or you can
Okay.
simply
Yeah.
in the Google. You just type what I did. See here in Google, I just typed robo analyzer.
Okay, I will share, sir. No problem. Can you share in WhatsApp after completion of your session? I will share that link to that person, sir.
Yeah,
That participant.
yeah. This I'm going to share
Yeah.
that
No
right now.
problem. Sorry, sir. Okay, thank you, sir. Ajay sir is tell that. Thank you, sir.
Uh,
Yeah. One more question. One more query.
yeah, yeah.
That one of the wonderful participant asked, what is the relation between the robo analyzer and RTA?
Okay, okay. Uh, okay. Actually, there is no relation between the RPA and the robo analyzer, but that software was taking too much time, and already I got delayed with this. My screen was not visible. That's why I avoided that. And in the next session, I will cover that one RPA. The theory portion I have covered, but the software portion I will cover in that
Sir,
session.
one more question. Can we get work in envelope in robo analyzer?
Can we get work envelope in robo analyzer? Uh, Work envelope we can just okay. Why not to try just for the other participants? Work envelope is the workspace means the maximum reach of the manipulator. So I don't think so that work envelope we cannot get. There is no option. No work envelope we cannot get.
Okay, sir. Thank you.
Okay, so
Other queries or respond or please write in chat box.
and regarding that RPA,
Okay, thank you, sir.
uh, okay, regarding that RPA is what just like suppose I want to send a mail to the recipients, okay, and suppose I want to get data from the internet, and that data suppose I want to send to the customers, okay. So we need to write a sequence, and we need to save that sequence, and then we allow, uh, you can say we allow to the system to do without the human involvement. So that is known as the robot. Okay, but here this is also robot. Yeah, it is also robot, but it is like a physical kind of thing. The robot will move its joints, but in that automation, that is known as a robot, but that is a cloud robot type of robot. Okay, there will be not means a sequence is being automated. The sequences are saved. Okay, then we are telling that you just follow the sequence. So that is the RPA, and the software exposure with the help of that UI path. Definitely, I will give exposure after this robot analyzer means next session. So in between, please allow me 2 minutes break because continuous speaking is somewhat difficult. So just I will come back after 2 minutes and see. And before that, I'm closing this. I was talking about, yeah, inverse kinematics. And what is inverse kinematics? Already I have told. Okay. See, in this inverse kinematics, how many solutions we are getting. Please observe how many solutions we are getting and why we are getting this much of solutions. But in the case of forward kinematics, we were getting only one solution. Here, in the inverse kinematics, we are getting multiple solutions. And the solutions depends upon the inputs like a joint offset values, twist angles, and a link lengths. Okay. So see, observe that how many solutions we got. Solution means to reach the same point. What are the various ways to reach the same point? Like solution 6 and see. If I click solution solution 6, then see the robot, and if I see, if I click suppose solution 1, then see the configuration. See, it got changed little bit, but the end effector positions and the orientation will be same for the all solutions, for the all possibilities. So with this, please allow me for 2 minutes break. I'm coming back, and if you have any queries related to this robo analyzer, you may ask, please. You can drop your
Sir, one more person asked, out of these
yeah.
8 solutions, which is the best?
Yeah, which is the best solution? So for that, we need to you need to opt some optimization technique. And the best in what sense? Like uh, suppose solution 8 is consuming less power. Uh, obstacle 8 is solution 8 is avoiding obstacles. So there are number of parameters. Okay, so based on that, means we need to apply optimization technique in that case. At this stage, we cannot know that which one is the best one. Yeah, just I'm coming back. Yeah, please 2 minutes break.
I am. Professor,
Yes, sir.
in chart box, one question is there. With
Okay.
respect to power torque, which can be best solution?
Just yeah. With respect to power talk, which can be the best solution? So for that, sir, we need to apply optimization technique. Here we cannot know. Here we can visualize only motions and the configurations. And by saying this only configurations, we cannot say which one is the best one. But one observation, like the joints movement should be lesser than, means as possible as it should be minimized. So suppose I'm once again suppose I want to know about the configurations of solution 7. Okay, so see solution 7 with respect to suppose solution 1, it got moved more. तो इसमें क्या होता है कि आपका मतलब जॉइंट्स में मिनिमम मूवमेंट होने चाहिए. So by this observation I can say, but accurately I cannot say. For that we need to apply optimization technique. And that optimization technique either maybe like a genetic algorithm that uh, one paper I have published that is on the that is based on the power optimization. So if you that I'm going to show you. Yeah. In my one paper, I'm just going to show you. Yeah. See, in my this paper titled "Power Optimized Motion Planning of Reconfigured Redundant Space Robot." So, for knowing that, I opted the optimization technique, and that optimization technique is a genetic algorithm. Optimization technique I used. Yeah. Okay, sir.
Yeah, okay, sir. Okay.
Oh, okay.
Please continue.
Okay.
Within 15 to 20 minutes, please close the session, sir. Time is already 4 is there.
Yeah. Okay. So these are regarding inverse kinematics and multiple solutions. Okay. Okay. And also we can visualize here, like if you select solution 1 or anyone, initial position. Okay. Like solution 1, I have selected initial position. Yeah, it is. Yeah, solution 1, initial position, and the solution 2, the final position. Now, suppose I change final solution 7, solution 7 I'm taking. So, now see, oh, it is not being changed. Okay, here, now I want to see solution 6 as initial values, solution 2 as final values. Okay, it got changed little bit. Okay. Also, yeah. So this can be visualized either by the motion with the 3D model or by the graphical way. Like a graphical way, for that we need to again analyze and then we want to know the graphical mode, and suppose we want to know about the joint motions like a joint 1 see, and suppose for joint 2, and the same for all the joint. So in this way also we can visualize. Okay, now inverse kinematics, this we did inverse kinematics values I'm taking. Now I wanted to jog joints. Okay. So in this is, yeah. Now what about this forward kinematics and the inverse kinematics we have done now, and this can be visualized by clicking in this way. Okay. Now we want to know suppose forward dynamics. Till now we were talking about like for Puma 4 or 5 we want to know. Okay. So forward kinematics we did. Suppose we want to know the inverse dynamics of forward dynamics. Okay. So firstly we need to learn the forward kinematics. Then but dynamics, and also in the inverse kinematic is it is always not possible to give the solutions. Always not possible to have solutions based on the inputs. Okay. Now we want the inverse kinematics. So by this we can understand the difference between the forward kinematics and the inverse kinematics. Here there is one more term, the force slash torque. Okay. In addition to that forward kinematics, now we will be able to know about the joint forces or torques required to move the manipulator. Okay. So in this way, the forward kinematics, inverse kinematics, and the dynamics we have done. Now what I wanted to show, yeah, we want to visualize the DH parameters. Okay, so in this way we can visualize the DH parameters by moving the coordinate systems. See how it is moving and translating. Moving means translating, and getting rotated. Okay. And regarding that transformation matrix, if I click update, the matrix will come here based on the inputs. Now we want to, yeah. Now suppose we want to jog the joints, means rotating the joints individually. Suppose joint 1, I am putting values of from 20, and accordingly the DH homogeneous transformation matrix will be changing. Okay, and see the movement, means rotations in the joints. Suppose I want to jog joint 2, joint 3, joint 4, joint 5. In this way, one can visualize the axis. Means sometimes we don't know which one is joint 1, joint 2, joint 3. Likewise, so after this jogging the joints, we can know. Okay. Also, we can record these sequences and can run. So, yeah. So with this, I would like to conclude. This Robo Analyzer is the very good software for the visualization of kinematics and dynamics, visualization of joints like either rotary or rhythmic joints. Okay, and also we can have the feeling of jogging, means moving the joints. We can demonstrate either through the 3D model or the graphs. So with this, thank you to all participants, and thank you, sir. If any
Any
queries,
queries? Dear participants, any queries? Sir, I think already in chat box in between the classes, they are asking questions, sir.
hmm,
Yeah, anyone please respond? No. Wonderful session. Any queries, please ask. Sir, I have one doubt.
yeah,
Can you tell me what is the main advantages in RPA for using your technology?
advantages, sir.
What you are using the robo analyzer? Can
Okay.
you can you explain how related to RPA in one or two words?
In sir, that visualization we can do.
Okay. Okay.
Yeah.
Thank you, sir. Thank you. Any other questions?
Ultimately, sir, in that means processes will be repeated.
Okay.
But, yeah, but मतलब, who is doing that? The processes means extracting data and mailing, replying emails, sending mails to the customers. So who will do this? Robot does. Okay, so by this robot analyzer, we can visualize the motions of the robots, visualize the kinematics and dynamics.
Okay. Thank you, sir. Thank you. Thank you, sir. Thank you, wonderful participants from the various states for listening and cooperating. And tomorrow morning, 9:55, the 9:55 will start the first session. I will share the details, all details in WhatsApp group. Okay. The attendance link is already posted in chat box and also group in WhatsApp group also. Please let me know any problem in your participation ID or anything. Please let me know messages or please call to me. Okay. Any other queries is there? Please respond, participants. Otherwise, we will end the session. Yeah, thank you, participants. And one more thing, participants, can you please mute your video and audio for entering the session? Yeah, thank you, Professor Vijay Kumar Dalla sir, for giving the wonderful session. Thank you, Professor. Yeah, thank you, one and all.